Hello everyone, I am Rajesh. In the last tutorial we have seen about GPIO programming and the blinking of LED on the freedom board. Now we are going to see about analog to digital conversion and digital to analog conversion using the on-chip ADC and DAC feature of this freedom board. Now before going to this ADC and DAC programming, we need to know how many registers are there for the ADC and DAC purpose and what needs to be initialized first before using these ADC and DAC registers. We have to see these things. For that we can refer to this one, and first of all we can see how many registers are there for ADC and DAC in this one. We can see that ADC has got many registers: status and control register, configuration register, data result register, compare value, status and control register, again offset control register. All these are registers for ADC, and similarly for DAC also we have many registers, and data low register, data high register, status register, control register. And before programming this ADC and DAC, the clock of this ADC and DAC needs to be enabled. To enable the clock for this ADC and DAC, we need a register called SCGC6, and it is found in SIM, that is called System Integration Module. And after initializing SCGC6, we are going to initialize configuration 1 register for ADC and SC2 for ADC. And for DAC initialization, it also requires the initialization of SCGC6, and as we will be initializing SCGC6 combinedly for ADC and DAC together, there is no need to reinitialize this SCGC6 again for DAC. SCGC5 is needed for this port E because the digital to analog pin is connected to this port E 30th pin. So port E 30th pin should be programmed as an analog pin prior to using this DAC feature. So this port E 30th pin should not be programmed as GPIO pin. And after this one, PCR will make this port E30th pin to be analog pin, and C1, C2, C0 registers of DAC needs to be initialized. After initializing ADC and DAC, we can send data to DAC and we can operate the ADC. For sending data to DAC, we have two registers: DAC low register and DAC high register. And DAC low register is of 8-bit type, DAC high register of 8-bit type, of which only 4 bits are accessible, and rest of the 4 bits are read as 0 by default. So on the whole, this DAC will accept 12-bit binary data that will be converted to analog voltage depending on the reference voltage connected to the DAC. And for ADC operation, SC1 register needs to be initialized with the clock source and channel selection, and we have to check for this COCO signal which is present in this SC1 register. COCO signal is nothing but conversion completion signal, and after this signal has got 1 on it, the result will be getting stored in result B and result A register, with which we can make the result to store in some other registers, our general purpose registers R0 to R12. Now we are going to see a simple program on this ADC and DAC. I have written a program for this thing. Here the main theme of the program is sending data to DAC, and that DAC will convert the digital data to analog voltage, and that analog voltage is being fed back to this ADC, and this ADC will convert the so produced analog voltage from the DAC to digital form again, so that we can have a near comparison between the digital value we are sending to DAC and the digital value we have obtained from the ADC. For this, I have taken first of all the addresses required for these registers, all the set of addresses, and here starts our program. This is ADC initialization. ADC initialization is started with the initialization of SCGC6, which is having a data underscore SCGC6, and that is 8800. If you go through the register of this SCGC6, register bits of this SCGC6, we are going to find that 100100, the 31st bit will be for ADC and 27th bit will be for the DAC. So those two are made once here, so that the clock is enabled for both of them. And ADC CFG1 register is initialized with 9C. This ADC SC2 is initialized with 0, and this ends the ADC initialization. And DAC initialization, for DAC initialization SCGC5 needs to be initialized, and port E PCR30 needs to be initialized, and DAC C1, DAC C2 and DAC C0. This port D PCR1 is used to initialize this LED, so that we can have this as an indication of conversion being taking place on. And after this initialization of DAC, we are going to initialize the port D as output port. So here we are using 02, so the second pin for which the LED is connected, blue LED is connected. After this, enable AD conversion. Now we are going to use our ADC and DAC from here. First of all, we are going to toggle this LED status. So WLED will be getting on and off every time the control comes to this location. After this, DAC operation, DAC data. So we have the DAC data as 0, 3Fs. So 3Fs in the sense, so the higher byte will be having only 4 bits and the lower byte will be having 8 bits. So on the whole, we are giving 12 bits to DAC. And this DAC data is loaded to R1, and for giving the data to DAC, FF needs to be given separately to DAC low register, and 0F needs to be given separately to DAC high register. So we are going to multiplex, or we are going to do an AND operation with FF, so that we can get these two data bytes out, and we are going to do an AND operation with FF00 to get these two hexadecimal numbers out, and we are going to give the two AND operation outputs to the DAC low and DAC high registers. So here we are going to AND the number R1 with the value in R2. So R2 is having AND1. So AND1 is FF and AND2 is FF00. So here we have R3 as AND2, and this will give the value of the higher byte. So and this higher byte is moved by 8-bit positions, right, so that it will be in the least significant byte position. After this, we are going to load the addresses of DAC low, DAC high, and storing the values obtained from the AND operation to these address locations. And we are going to now initialize this ADC SC1. ADC SC1 is made 00. So 00 is for the channel selection DADP00, and it is a single-ended analog channel. And we are going to have a number move R3, ATH. So ATH is used for the checking of the COCO signal. If we go through that ADC SC1 register, we will be seeing that. So all are zeros here, and here it is 0, 0, 0, 0, 0. So these channel selection bits 43210 is selected as 0, 0, 0, 0, 0. So 0, 0, 0, 0, 0 is pertaining to the DADP0 as the analog input, and whenever these bits are given with 11111, the ADC module gets disabled. Now having it been given all zeros, now the ADC conversion will start on its own, and this COCO signal will be set to 1 whenever the conversion is complete. So to check this COCO flag, this needs to be equal to 1. So if it is 1, 0, 0, 0, 0, we are going to get ATH. And the same way we are going to do here, R3, 80, and we are going to compare this 80 with the obtained R2. So here we are loading the R0 with ADC SC1, and we are getting back the value present in ADC SC1 to R2. So whenever the particular COCO bit rises 1, this R2 will contain ATH. So ANDing R2 and R3 will give 80, and with 80 will give only 80. So if it is not equal to 0, it will come down. So if it is equal to 0, it will again test for the signal to become 1 until the COCO signal becomes 1. So whenever the COCO signal becomes 1, it will come down. Now the ADC result will be stored in the B and A register. You are going to get those values into R0 and R5 respectively. And after that we are going to disable that ADC by sending all ones to the channel selection bits. So 1 1 1 1 1, it is 1F. So here I have chosen a data FFF that is going to be decremented by 1 for each and every operation. So now R1 is getting reduced by 1 and comparing with 0. If it is equal to 0, again we are going to do that thing. If it is not equal to 0, we are going to do directly the DAC operation. Here comes our do label. So and again label is here. So whenever that count becomes 0, then the port D LED is going to be toggled, and again the process is going to be started from first, and intermediate steps are this B do, and it will come here. Now we are going to dump this program into the freedom board, and we are going to see how it is going to be work.